Critical links and unlinks.
Jason, thank you, and thank those of you for coming out. I thought I'd do this the old-fashioned way. I want to talk about something that's a little more speculative, or as Roman Boni said, aspirational. There are two problems I want to consider, and they're both related to topics that came up this morning. The energy that Mike Friedman and Zhenghang Wang and Xingzhu He studied, that was introduced by Jun Ohara, the Mobius energy, and also the rope length. So I want to look at these, and I guess since I'm writing behind this screen here, I hope I won't use that anymore. So the Mobius energies we saw in Philippe's talk this morning is a scale invariant energy, in fact, invariant under inversion, that if I take a curve, gamma, I can go into R3 or R4 or into the 3-sphere if I think of this sitting inside of R4. And remember, it's defined, this energy is the 2 version of the energy he defined for a curve gamma. It's defined by integrating, in fact, if I parameterize by arc length, I can simply think of this as being essentially integrating the distance between 2 points squared, and I can think of that as mapped into R4, okay? And then I'm integrating with respect to arc length, and so that means gamma prime is, gamma prime has length 1, so I'm simply integrating this. Now, of course, that integral, this is a double integral over the torus, that doesn't converge near the diagonal. This has a little bit of a problem near the diagonal. And so it's regularized in various ways. And one way I'd like to think of regularizing that is not to subtract off the distance of the 2 points along the curve, which is what Philippe and others have done, of course. But I'm going to do a slightly different regularization, which is to subtract off what you might think of as the energy of the round circle itself. So this is infinite, and I'm going to really subtract off to regularize it, subtract off the energy of the round circle. So let me simply write E of S1 for that. These are both infinite quantities, if you like, but this is, in effect, I'm comparing I'm thinking of the circle with the same length as whatever length I took for this curve, and I'm subtracting off an integral that would compare those distances and look at the 1 over that distance squared. So let me write this a little more. If I call this distance, let me call this distance d between these 2 points. And in effect, what I'm doing is I'm subtracting off this distance here, so sort of the distance between S and T, where I measure it straight across as opposed to along the arc length, squared. Okay? And the result, of course, of that is that the energy of the round circle, tautologically, is 0, and that's the absolute minimum, okay, for that. So that's not a proof that it's the absolute minimum, but it's a nice way to think about this. Okay. So one of the problems has been what other links can we actually identify the absolute minimum for? And this is a problem that Friedman and Wang considered in their paper around 1993, which is for the round circle, we know the minimum. So this is the absolute minimum among all closed curves. And of course, as we know, one of the interesting problems is whether there are any other critical points among unknots. If we could solve that problem, this would give us a nice analytic proof of something known as the Smale conjecture, or Hatcher's theorem, about the space of unknots, or more generally the space of diffeomorphisms of the 3-sphere or of R3, or a number of equivalent formulations of it. So this would lead to Hatcher's theorem, or the Smale conjecture, the Smale-Hatcher theorem. That would be nice if we could do that. We don't have anything there. But one of the questions that Friedman and Wang asked was about the space of Hupf links, okay, about critical points among Hupf links, okay? So what's a Hupf link? Well, let me remind you that geometrically we can think, in fact, you probably know what a Hupf link is. I tried to start drawing one. I got about as far as the first component, but doesn't really matter which way I put it on there, I guess. So, so Huplink, geometrically, thank you, is a collection of unknotted circles that there I have one of them, and I can think of them as sitting on the surface of a torus, and I didn't actually draw the next one in, so you have to use your imagination. I can think of just sliding them along the torus, and in fact I can foliate the torus with a bunch of Huplinks. These are 1-1 curves in the torus, and whatever number of curves I put in there, that gives me a k-component Huplink. So if I went halfway around, then I'd get a curve that I didn't draw in that links it exactly once if I pick the orientations right. So that would be the usual Huplink. And I'm interested in k-component Huplinks. And you can think of these geometrically, of course, if I think of the three-sphere not in R3, but inside of, excuse me, not in R4, but inside of C2, then I can think of these as orbits. Okay, these are orbits, of course. These are the Huplink, a k-component Huplink is an orbit of k points. So this is an element of here. I'll call it Hup k. This is a geometric Huplink. It's an orbit under, well, the action e to the I t, say, times z, e to the I t times w. This is the set of zw. Okay? And if I pick, so if I pick basically a k-tuple of points that are vectors that are independent vectors, okay, then I get these k Huplinks. That's one way to think of it. So for example, if I take just the vectors 0, 1 and 1, 0, I would get the two-component Huplink, and more generally, I would get a k-component Huplink. So this gives these two orbits give rise to the usual picture if I think of that projected stereographically back into R3. Okay. Now, in general, these orbits, okay, these orbits I can think of course, if I take one way to think about this, of course, is take the ratio of these coordinates, and then that gives me the so-called Hupf projection. This is where this comes from. So I can think of the Hupf projection, right, from the 3-sphere down to the 2-sphere, which basically takes ZW and gives me the extended, think of this as the extended complex number, okay, in the 2 spheres, the extended complex numbers. That's one way to think of the Hupf map. And of course, a Hupf circle, right, because e to the I, t to the I, t, I'm taking the quotient of those two things, that gives me the same point down in the sphere. So a Hupf link I can think of as simply a collection of points. For example, 2 points. If I take 2 antipodal points, then their pre-image upstairs is, of course, the simple Hupf link. And more generally, if I've got k points, then I've got a k-component Hupf link. So I have more components there. And the Möbius energy turns out to be very simple on the Hupf links. The Möbius energy is this double integral, but since the function is invariant under rotations, you can turn this double integral into single integral. And for the case of Hupf links, it turns out this energy, the Möbius energy of the Hupf link, if I've got components gamma 1, gamma 2, up to gamma k, so gamma 1 is a geometric Hupf link. In this sense, it turns out this is exactly an energy that can be computed in terms of the Hupf projection. So if the gammas, if this is gamma 1 and gamma 2, and these project to P1, P2, or more generally up to gamma k to some points P3 up to pk, then this turns out to be exactly what I'll call C, P1 up to CPK, which is the Coulomb energy. In fact, it's 4 pi times the Coulomb, 4 pi squared, excuse me, times the Coulomb energy, where I simply take the distance in the sphere. So I take the straight line distance in the sphere between these points. So for P1 to P2, for example, that distance would be 2. And what I take is the 1 over that power of this distance. So pi pj to the first power for I not equal to j. Okay, so I take that sum, double sum over those, and it turns out that's exactly the Möbius energy of the corresponding geometric Hopf-link upstairs. Okay, so the question that Friedman and Wang asked was essentially, if I take, let's consider the case k equals 2. Okay, well, we know for the geometric ones that the lowest energy configuration, of course, is where the points P1 and P2 are antipodal. That would correspond to two great circles that are maximally distant on the 3 sphere, or 2 round circles in 3 space that are at some actually funny angle that are not quite at right angles. And that problem was an open problem. They actually had some partial results in the case where if you assume one of the curves is a round circle, then it turns out that you can think of the Möbius energy for a general Hopf-link, for one that's both components are free to move around, but I fix one to be the round circle. Then it turns out that Möbius energy turns out to be a length in a certain Riemannian metric, a metric basically on the circle cross hyperbolic plane. And in that, under that assumption, you could show that in fact the round Hopf-link coming from a pair of geometric Hopf-link from a pair of antipodal points gives you the minimum. But it was only this spring that Ian Agel, Fernando Coda Marquez, and Andre Neves were able to prove that in fact this is this case where P1 and P2 are antipodal is the minimizer. Okay, so that sort of begs the question, and I want to now. So what happens for k bigger than 3? All right. So for k bigger than 3, again we've got a space of we could look at the space of these curves. Okay. So for k bigger than 3, we could look at the space. I might call this Hopf k. These are the space of curves that are isotopic to a given Hopf-link, and that so it's an infinite dimensional function space. And let me be, since I have only a limited amount of time here, the ideas that come out of Hatcher's proof of Smale conjecture leads us to recognize this. I'm going to be a little bit careless. I'm going to be essentially there's a deformation retraction from this space to the space of round Hopf-links. Okay, so one expects that this space somehow the critical point theory for the space of for the Möbius energy on the space of all Hopf-links should be reflected in the Coulomb energy on the space of these. Now I think Paul's here. I know Paul and Natia have worked a little bit on a related problem here. I just want to quickly point out that for 3 or more, we don't know whether there are other configurations that are potential local minima, and there may be, of course, lots of high order critical points. But of course, for 3 points, the Coulomb energy has been analyzed pretty carefully even 100 years ago or so, when Thomson was making this as a model for the atoms. And for 3 points, of course, the minimum for Coulomb energy on the sphere for 3 points is 3 equatorially placed equidistant points. And in that case, we'd like to know whether there are more general configurations. And if I take a large number of points, this is some work John Sullivan and I did about 20 years ago now. We studied all the possible critical points of the Hopf energy numerically, so stable and unstable points. And we were a little bit surprised to find that with 16 points, thank you, with 16 points, there are actually 2 different local minima configurations. Okay, so that suggests that in fact the Möbius energy is not a nice perfect Morse function on the space of Hopf-links, because we don't have a proof of this, but we expect that in fact these are 2 stable configurations in fact, upstairs in the space of Hopf-Links. These are two stable configurations for electrons on the two-sphere. Very, very close to each other. You might notice less than 1 part in 10,000, the separation in their energies, and therefore their Möbius energies. Okay, so that was part 1. Let me quickly jump to part 2 of this. Part 2, I want to consider a little bit about rope length. And the reason that there's an eraser. So the reason why I think this problem about Hopf-Links is tractable is there's a nice finite dimensional model, which I've only hinted at, for the space of sort of the homotopy type of the space of Hopf-Links, which is the essentially the configuration space of points. And the space I want to look at now is something that I'm going to call McCool, because I like that name. No, McCool is really this. McCool studied a group which is the fundamental group of the following space. This is the McCool K is the space of unlinks of K components. So this is the unlinks, trivial links. Okay, so again, the case K equals 1 for McCool space, and I'm going to think of this as in R3. And I want to look at rope length on this. All right, now again, this is a little bit, so this is work that I've been doing over the years with Jason and other people. Ryan Budney has been contributing a bit to the topology on this. So I just want to show you a little bit about what McCool space looks like. So these are the unlinks of two components, and thank you. So obviously there's an unlink of two components at the bottom. All right, and it turns out that for rope length, using ideas that Matt, if we want, we could use ideas that Matt brought in, or we could do explicitly just checking our force balancing conditions for criticality of rope length. There's this sort of picture of what the low energy critical point should look like for rope length. All right, now I have to be a little bit careful, and that's why I decided this is going to be hard to actually exposit either in transparencies on the board or in a higher way. So we have to really keep track of things like orientations and which component is there. And the number of critical points, when you keep track of that, multiplies very quickly. All right. So here's at least a picture of 3 low energy critical points, and conjecturally, that's it for energies down this low. Presumably, if there are any other Gordian unlinks, Gordian places in the McCool space, they're way up in the energy. And the thing is, the problem is that there's actually a big family of these. There's a big equivariance we need to keep track of. So for example, the space of the set of critical points that have the type that looks like a kind of a, it's not quite a Saturn ring. It's a Bialy, a tight unknot, together with a stadium curve wrapping around it. So the blue curve on the left in the middle row there is the absolute minimum for length, and there's the stadium curve that wraps around that, around the belt. And there's really an SO3 worth of those, okay, all the rotations of those, and there are these 2 orientations. So this space gets a little bit complicated as we try to work out the critical point theory. There's a nice theorem, though, that is about to appear by Tara Brendel and Alan Hatcher, which again gives, so this should appear next year in Commentary, which again gives a model for this McCool space. Okay, so McCool K turns out to be, again, has the homotopy type of, I think they call it R sub K, or it's a space of round rings. And that, again, is a nice finite dimensional model. And since I'm out of time, let me just show you, whoops, thinking through what that model looks like, what the, so this is certainly, these critical points are consistent with the homotopy type of that model. For McCool 3, and I'm out of time, we have, well, at the bottom we have the 3, obviously, that's the minimum for energy, that we can prove. And at the top of this picture, I've got 3 concentric rings. And then in between, I have this collection of what we might think of as middle index critical points. And I was going to try to draw for you the flow lines that connect them, but these are roughly in the order of the critical points that appear. And one of the questions, though, is whether there's actually an unusual critical point like this, which when I pass that loop through it would give something like this intermediate point. And just to show you that sometimes we need to make physical models. This one in the middle is that critical point that I'm suggesting there. Here, a few I'll pass around for fun. So the guy used to play first base, and here's one for Jason. All right, thank you very much. Sorry for running over as usual.
Thank you.
Jeez, this thing is a blower.
So I don't want to delay our coffee, but if there's a question or two for our speaker.
When you say critical points, Robert, they're probably saddle points, aren't
They're settled. So, for example, the one that's let's take this one here. That's actually a derivative of the cool 2 space, the one that has a 2 concentric rings in the isolated. That point should have index 3. Okay, so there's an easy deformation that the second order changes the length to second order. Namely, I just push the big one off. But then there's a 2-dimensional family also that if you just think about geodesics on such surfaces, the family that rotates off this way or rotates off that way, that also has negative second variation for length. So that's just in that level. And the higher up you go, those become fairly high index. So I think, I didn't check the dimension, but I think the top one is index 6 in that picture. Okay.
Did you say that the Coulomb energy isn't a Morse function, or did I?
It's a Morse function. It's not a perfect Morse function. So this space is connected. Space of it's on the space of points in the configuration space of points in the 2 sphere. It's a connected space, but so you only need 1 local minimum, but those are 2 local minima. That's the first case we know. John, I think it's the first case we have 2 different local minima. So presumably,
we only know numerically.
yeah, it's and as you can see by the energy there, they're quite close to each other. So you might think, but they're quite different symmetry types. So to the extent to which you believe numerical arithmetic, high precision numerical arithmetic, this is a counterexample to it being a perfect Morse function. Okay.
Well, let's thank our speaker again.